Hello everyone, and welcome to tonight's session on how to choose between SN1, SN2, E1, and E2 reactions. Before we begin, just quickly let me know in the comments, what brings you here today? Are you preparing for your Orgo final, which I presume you either have an exam coming up or your final exam very soon? If yes, Orgo 1 or Orgo 2, and also let me know where you're tuning in from. Some quick housekeeping before we begin. I know that you are going to want to write everything down. Don't worry about it. All you have to do is go to leahforsci.com/OrgoLive. Right there. Yep, just grab the link on the screen. It's also in the pinned comment. Sign up over there, and I will send you a copy of tonight's session notes, a link to this recording, and you'll be able to go back and review and make sure that you are fully caught up. So just click that link and you will be all set. Nadia has a final exam in 2 weeks, tuning in from Chicago. Nadia, it is good to see you. All right. There is a delay, so if you're typing comments, just give it a couple of moments. Nura from Vienna, Austria. Oh, wow. All the way around the world. Humu is preparing for third Orgo exam from NYC, just down the road. I'm about 45 minutes from the city. So we're neighbors. Han is the first Orgo 1 first time in college. Okay, that is awesome. All right, so let's switch on over to here. And if you are just joining us, welcome, welcome. Let me know in the comments where you are tuning in from. And let me get our first reaction on the screen. All right. Oh, a couple more. Sabitri from Maryland, Sonora. Where are the notes? Sign up, and once I'm done, I'll save the notes as a PDF and I will send it to you. Aaron has an exam tomorrow. Well, Aaron, if it's on this topic, you will be very, very happy because I will have not just these notes for you, but so much more practice. Gina is also from New York. Looks like we have quite a few neighbors here. User using preparing for my doctorate. I'm assuming you meant doctorate exam, which is in December, from France. Wow, wishing you the best. Guillermo from Chile. Looks like we have a lot of students from everywhere. This is so exciting. I mean, guys, think about it. I'm sitting here in my home in New York, and you guys are just tuning in from all over the world because, well, we all have one goal here, and that is to figure out how the heck do you choose between substitution and elimination reactions. If I give you a molecule like this and ask you to react it with NaOH and tell you to figure out if it's going to undergo an SN2 or an E2 reaction. Now, there could be other conditions, depends on the situation. The answer is both. It can do both reactions. What if instead I change the reaction conditions and I tell you to react it with H2O and once again ask you to choose, will it undergo an SN1 this time or an E1 reaction? And again, depending on the situation, depending on the reaction conditions, again, we can have both. So the question is, how do you decide? What most students will do, and let me know in the comments if this is going on in your class as well, you use some kind of crazy flow chart that has if this, then that, but then this, then that, then that. And it's just all over the place, very confusing and not very helpful when you're under pressure. If this is what you've been given, if this is how you've been studying, and you want a faster and yet somehow also more logical way, that's exactly what we're going to cover today. And don't worry about writing everything down. For a copy of today's notes, just go to leahforsci.com/OrgoLive. Even if you're watching the recording, you sign up and you'll get an email with a link to this and so much more. What we're going to do here is, instead of just following some crazy things that we memorize, which frankly, on an exam, if you have a lot to memorize and you're under pressure, I always forget. So I need something simple. And the only thing I'm going to ask you to memorize is this 4-part checklist. And I will show you how this checklist is going to trump any flowchart and help you come up with the reaction. So we're going to look at the alkyl chain. I'll explain it in a moment. The attacker, the solvent, and the leaving group. These are the only things you have to memorize. And as long as you understand how to analyze this, you are good to go. So let's break down the checklist, starting with, I'll keep it here so you can remember what we're looking at, starting with the alkyl chain. When I'm referring to the alkyl chain, I'm specifically looking at 2 or more, but 2 types of carbons, and that is as follows: the alpha and the beta carbon. If I have a carbon chain, and in the context of substitution elimination reactions, I have a leaving group that I zone in on. The leaving group is what I care about. The carbon holding the leaving group is the alpha carbon, and any carbon directly attached to that alpha carbon, that is my beta carbon. So in this case, I have 2 different beta carbons sitting on that same alpha carbon. What am I looking at with the alpha and beta? And just to clarify, the alpha is the one that holds the leaving group. That's supposed to be holds the leaving group. And beta is next to, directly connected to the alpha carbon. So let's go with one at a time. For substitution reactions, I only care about the alpha specifically. And what I'm looking at is, does the substitution of the carbon holding the leaving group tell me anything about reactions that I can keep or not keep? And with elimination, it's less important because I also care more about what's around it. So I want to ask the question 1, can it form a stable carbocation? The reason I care about the carbocation is this is how I know if I can have an SN1 or E1 reaction. I need a carbocation intermediate, and if it's too unstable, for example, a methyl group or a primary, then it's not going to happen. So this is a yes/no question. And if no, this is critical, then I can rule out the SN1 and the E1 reaction, which is really, really important. The next thing I look at is the exact opposite. To form a carbocation, I need it very substituted. That helps me with the SN1 and E1. But if it is substituted enough, is it too sterically hindered? Is it too crowded? And specifically, is it a tertiary carbon holding the leaving group? Because if I had a tertiary carbon holding my leaving group, I can't bring in a nucleophile to attack at that position. And that means no SN2 reaction. If yes, no SN2. So this information is going to be the starting point of being able to rule out some of the reactions. And the more you rule out, the fewer options you have, the more likely you are to come up with the right answer. That covers the alpha carbon. What about the beta carbon? For the beta carbon, I'm looking at, well, question number 1, a lot of students completely miss. Do I have a beta carbon? And specifically, does the beta carbon have a hydrogen? I cannot tell you how many times a student will tell me the answer is elimination, and there's no beta carbon. So let me show you what I mean. That way we're not speaking in hypotheticals. If I have a situation where I'm given a CH3 Br, and I reacted in some kind of conditions, and I want to do an elimination reaction. No matter how good a base I have to attack it, no matter how good my solvent is for an E2 reaction, fact of the matter is I only have 1 carbon. That 1 alpha carbon does not have anywhere to attach to if I were to make a pi bond. And that means if I have no beta carbon and no beta hydrogen, I have no elimination. This comes up a lot if I have tert butoxide. And students see tert butoxide reacting with anything, it has to be an E2 reaction. This cannot be an E2 reaction. So question number 1, do I have a beta hydrogen? If no, then I have no E2 or E1. I can have absolutely no elimination reaction. And then if I do have more than one option, so we want to ask, can I form a stable pi bond or a more stable pi bond? If I have options, I do want to keep in mind Zaitsev's rule, which I'll show you when we look at the elimination reaction, to see if I have something more substituted or less substituted. I can choose my major and minor product based on, I'll show you a shortcut, the beta carbon and the beta hydrogen, rather than having to draw them all out. So far with me, we went through one item on the checklist. If yes, and if you're not subscribed yet, what are you waiting for? Go ahead and hit that subscribe button. I want to see if I can reach 1 million subscribers in the next couple of years. So help me out. Go ahead, hit subscribe, and we will start looking at number 2, and that is the attacker. The biggest question I get from students on this topic, and let me know if this has been your question, is how to tell the difference between a nucleophile and a base. Let me know if the bane of your existence has been this one question, figuring out the difference between a nucleophile and a base. Let me see some smileys in the comments if you've been struggling with that. Instead of answering the question, I want to challenge you with a counter question. What if I showed you that you didn't have to worry about it? What if I showed you that the way to solve this topic is not to look at the difference between a nucleophile or a base, but instead to look at how the attacker reacts? So you're not on board yet with me. That's okay. Give me a couple of moments and we'll reevaluate, because I want to ask you this question. If you see a molecule reacting with OH minus, is it going to undergo substitution or elimination? Is OH minus a nucleophile or a base? Think about it. OH minus, nucleophile or base? I know there's a delay in the chat, so let's quickly detour and talk about what we're actually looking at. A nucleophile comes from nucleophile, which means nucleus loving. If something is nucleus loving and the charge of a nucleus is positive, something that loves the nucleus is going to seek out the nucleus. And so I think of a nucleophile as a molecule that is positive seeking. What is going to seek out positive? Well, wouldn't it make sense that something negative or partially negative is going to seek out positive? That means my nucleophile is negative or partially negative. That's for the substitution reactions. When we're looking at the elimination reaction, we're looking at a base. Now, there were 3 definitions that you learned: Arrhenius, Bronsted, Lowry, and Lewis. In the context of elimination reactions, we're looking at the Arrhenius/Bronsted Lowry, depending on the solvent. And if you remember those definitions, a base was something that would accept a proton acceptor in whatever the solution is. And if we think about a proton acceptor, the proton is positive. What is likely to accept a positive proton? Something negative or partially negative. That is a base. A base is negative or partially negative. So if I look at these two, the nucleophile is negative or partially negative. The base is negative or partially negative. And the answer is what? Which one? So let's see what you came up with. If you said nucleophile, you are absolutely correct. If you said base, you are absolutely correct. OH minus is a very good nucleophile and a very good base. It simply depends on the context of the situation. First, some nice things, which I really appreciate. Thank you. And thank you, 124%. Amazing. I love hearing stories like this because I love teaching. And I just sit here and teach. It's up to you to watch, to take notes, to put in the work, to practice. But to come back with stories like that, that means you put in the work, and I'm very, very proud of you. To understand the idea that OH minus can be a nucleophile and a base, we use a real-world example. I have a toddler who I talk about a little bit too much. To him, I am a mom. I have a husband, and to him, I am a wife. Does that make me a mother or a wife? Well, it depends on the context of the situation. It depends who I'm referring to. I am both. So the same thing with OH minus and the same thing with a lot of these other molecules. So let me show you what I mean by context of the situation. In the opening problem, I gave you a molecule that looked like this with a bromine, and I will show you the same molecule with two different reactions. If I bring the OH minus to attack at the carbon holding the bromine, this is a nucleophilic attack. I attack the carbon, kick out the bromine, I get a direct replacement. I swap the Br for an OH minus. That is the substitution part of nucleophilic substitution. In this case, OH minus is acting as a nucleophile in the SN2 reaction. But if instead of grabbing or attacking directly at the carbon, the OH minus is going to choose the hydrogen, collapsing the electrons to kick out the bromine. In this case, OH minus is acting as a base to grab a proton, kick out the electrons, kick out the bromine, and that means it is acting as a base for an elimination reaction. So if the molecule directly attacks the carbon and stays stuck on, so let me show you the product for both so you can see. If the incoming attacker remains attached like this, that is a nucleophile, nucleophilic substitution. If the attacker does not remain attached, instead it just grabbed and ran, giving you a pi bond, that is the context for an elimination reaction. And this is why I said the question is not about the difference between a nucleophile or a base. The question is really about figuring out, will it be a strong attacker or a weak attacker? So I know if I'm going the 2 route, SN2E2, or the 1 route, SN1E1. If this is starting to make sense, but you're a little confused, let me see a thumbs up in the comment. Thumbs up meaning I'm starting to get it. And as a reminder, what I'm showing you today, this is going to be the starting point. I want to set you up with what you're going to use to practice, but then I want you to do I do want you to do that. I want you to do tons of practice, which is why I have a brand new substitutional it's been a long day. My toddler has not been feeling well. Substitution elimination midterm practice worksheet, not available on my website. All you have to do is put worksheet in the comments, and I will send you a link so you can download it for free and practice tons and tons. And it took me 3 hours to solve that thing. So that is how many practice problems you have there. And let's continue. So we have our big picture definition. Let's take a step back. Joshua, we're going to get to that because that is really, really important. So first, as a reminder, we want to ask a different question. You want to ask, is it a 1 or a 2 type reaction? Kind of ran myself into the corner there. Is it a 1 or 2 type reaction where 1 is SN1 or E1 and 2 is SN2 or E2? So the question is, what is going to give us that kind of difference? When we're looking at a 1, let's start with a 2 type reaction because we kind of started there. For a 2 type reaction, we're looking at SN2 and E2. These are reactions that happen in one quick fell swoop. The nucleophile comes in, attacks, kicks out. The base grabs a hydrogen and kicks out. These are very fast reactions. We have no carbocation intermediate. And that means in order to carry out this kind of reaction, I have to have a very strong attacker. A strong attacker is very reactive. What makes a molecule strong? What makes a molecule react? What makes a molecule want to do anything? Strength is measured by instability. If something is happy, it's stable, it's unreactive. If it is unhappy, it is unstable and therefore reactive. What makes a molecule unhappy? What makes a molecule reactive? Charge. So your strong nucleophiles and bases are typically going to be charged. You'll have your OH minus, your RO minus, for example, methoxide, ethoxide, tert butoxide, and a couple of other molecules. You'll see some S minus, you'll see some things with resonance like that. The charge is what you're looking at. Where, on the other hand, if we're looking at a one-type reaction, and I'll go through the mechanisms soon so we can tie this all together, we're looking at SN1 and E1. These are the slow reactions. If you think about the mechanism for these reactions, it has to wait and wait and wait. And eventually a carbocation will form. And only when that carbocation finally forms, then the nucleophile can come in and attack. So this is the one with the carbocation intermediate. And anytime you see carbocation intermediate, I want you to think slow reaction. Do you think a strong, reactive, unstable molecule has the time or patience to wait for a carbocation? Absolutely not. Never, ever, ever show me an O minus and a carbocation. They are opposite worlds. The attacker in an SN1 or E1 reaction that has the patience to wait for an intermediate is because it is a weak attacker. And the weak attacker has no choice but to wait. What makes a molecule weak? It's a molecule that is stable. It has no desire to react. And if it has no desire to react, it's just going to hang out and chill and watch TV and scroll on its phone, mind its own business. And if there happens to be a carbocation that finally decided to form, yeah, it'll jump on that opportunity, but it's not in a rush, and it's definitely not kicking anything out. So what are we looking at with our weak attackers? We're looking at water and alcohol and an amine, just neutral solutions with no charges. The biggest question for the attacker, one type or two type? If you're with me, I want to see some thumbs up in the comments. I did see a question, a clarifying question, because of course in organic chemistry, it's not going to be, here's a concept, it's so easy, yay, let's go apply. No, there's going to be like a gazillion exceptions. 2 gazillion exceptions. My son's ability to count at this point is 1, 2, 3. He gets tripped up until 30, and then so many. So many is a very, very big number. And that's how many exceptions there are. But we're going to try to simplify it here as follows. The few situations where you have one over the other. Let's title this exceptions. Okay. Situation number 1, halogens. The thing about halogens is that they make very good nucleophiles, but weak bases. And the reason for that, we're not talking about fluorine. Fluorine is too small, too reactive. It's not going to play nice in the context of reactions, so you're not going to see it. Nikki, I don't know if that works for me. Awesome. So a halogen, if you give it a charge, it's so big. And what it'll do is just distribute that charge and carry it very, very comfortably. It's really good at holding that charge. And that means it has no desire to attack. So think about, I don't know, you're walking, you have to move out of your dorm because the semester is over, and you need help carrying your furniture. Are you going to help your friend who's about 90 pounds on a good day that can barely pick up a chair? Or you're going to find your 250-pound, works out at the gym for 3 hours every day, has no, could probably pick that chair up with his pinky finger kind of friend to help you carry your furniture. The halogens are so big that even though they have a charge, it's not a problem for them, which makes them very weak as a base because they have no desire to grab a hydrogen. But it makes them very good as a nucleophile, because the idea with the nucleophile is it's carrying the charge, it's perfectly okay. And then it sees a carbocation, it sees a positive charge or a partially positive carbon, whatever the situation. And now all that negativity that was nicely distributed gets concentrated in one area. All the charge just moves to that one part of the molecule. The way I want you to think about it is, imagine a school bus. The school bus is driving along, and then somebody says, a unicorn over there. And all the kids rush to one side. So instead of having kids, just dozens of children on both sides of the bus in their seats, everyone rushes to one corner. I don't know if this will happen actually, but I'm going to imagine the bus is going to tilt a little bit to that side. I don't actually know if the bus would tilt, but imagine like a cartoon situation where they all just do. And so if you have a molecule like this, or let's show it something like this, and it'll probably be easiest to show it like this with a CH3Br or a CH3 leaving group. The leaving group being a halogen, which is your typical leaving group, is going to be pulling and pulling and pulling on the electron density away from carbon, making carbon partially positive. If you have a halogen right there, which is perfectly happy, and now all of that charge density concentrates in one area, that makes it a good nucleophile. So halogens make good nucleophiles and weak bases. Another type of molecule that will react in a very similar way is a molecule that has a lot of pi bonds or has a lot of resonance. So these tend to be good nucleophiles, but not very good bases. So for example, a CN minus, a CCCC minus, a molecule that has resonance like this, and 3 minus. So notice how these all have a lot of pi bonds. They may or may not have resonance. These tend to be better as nucleophiles, not very good as bases. So nucleophile over base, and the same thing here, nucleophile over base. And this is all due to the ability to polarize. It can polarize, which is what we're looking at in the context of a substitution reaction. On the flip side, though, we have another group of molecules, and that is a big, bulky base, which I like to call the triple B. And the one you're going to see in organic chemistry 1, typically, is tert butoxide. It's written many, many different ways. T-but-O- is one common one. Tert butyl oxide. Oxide tells me I have an O-. The tert butyl is the R group that's attached to it. And if you draw this out, you'll notice CH3, CH3, CH3. This thing is huge. It is very, very big. It's very, very bulky. We already hinted that bulk is an issue for SN2, and so this is too bulky, L, for an SN2 reaction. So if you see a tert butoxide, I want you to think immediately, very likely, an E2 reaction. Another one that you may come across, but more in Orgo 2 than Orgo 1, is LDA. The L gives us a lithium, which is a spectator ion. We don't care about it. But the Da is the base portion. It's a diisopropyl amide. LDA, lithium diisopropyl amine. Well, it's a negative amine, so that would be an amide. I'm having a brain fart here for a moment. LDA stands for linear discriminant analysis. Let's try that in organic chemistry. Diisopropylamide. I don't know why I was having a brain fart on that. I've been doing this for over a decade, and I still randomly forget some things. All right, so we have these two that will act as big bulky bases. And if you see them, they prefer to do an E2 reaction rather than an SN2. Because in an SN2, as I just showed you here, the nucleophile, which is this thing, has to get all the way into the molecule. Now, in this one, it's not a problem because it's just a CH3Br. But if we look back, for example, at, well, that's not the opening problem. Here we go. Something like this, you can't have a massive nucleophile coming in and attacking there. This molecule is too bulky, too hindered. And so it's going to be easier for this thing to just take a step back, pluck off a hydrogen from the side, and do an elimination reaction. All right, so that covers the second part of the checklist. Let's move on down to number 3, and that is the solvent. Now, as you're working through the checklist, most of the problems will already be solved just by looking at the alkyl chain and the attacker. But if you do have to keep going, take a look next at your solvent. And there are 2 types that you're looking at. We're looking at polar, protic, versus aprotic. So what on earth is a protic solvent? What is it that we're looking at? Protic kind of sounds like proton. And if I take a proton and I put an electron with it, I get a hydrogen atom. That's all hydrogen is, a proton and an electron. So the protic solvent is a solvent that is capable of hydrogen bonding. The way you remember how to identify a solvent that does hydrogen bonding is to ask a very simple question. Do you like to have fun? Do you like to have fun? I like to have fun. I was about to say I don't remember what fun is, but these days fun is just whatever my toddler finds funny. So we're watching this. I saw this video on Instagram where the woman says if your toddler can't fall asleep before bed, you want to tire them out. So we have a new game that I got from her, and that's the run and touch it. So I pick something at the other end of the house and I say, can you go run and touch the door? Go run and touch something over there. So, and my kid was just running around touching everything. It's like the silliest game in the world, and he loved it. So that was my fun for tonight. That was actually a lot of fun, just so giggly. FON is what we're looking at to identify if the molecule can do hydrogen bonding. And specifically, I'm looking to see if the solvent has a hydrogen on this atom. Now, I already told you you're not going to see fluoride in these reactions because it's way too small, way too strong, way too reactive. We're just looking at ON. If the hydrogen is on oxygen or nitrogen, then it's a protic solvent. If the hydrogen is on a carbon, that's not fun. Carbon is boring. Carbon is no fun, no hydrogen bonding. So what kind of examples would we have for a protic solvent? Oh, how about water, alcohol, an amine that has hydrogen. So for example, RNH2, R2NH, NH3. Notice that each of these have hydrogen sitting on oxygen, hydrogen on nitrogen, hydrogen on nitrogen. These are protic solvents. But if I have a solvent that does not have an O or N holding the hydrogen, then I have an aprotic solvent. And the 5 that you want to recognize or memorize are DMSO, DMF, ether, I'm trying to remember them. Help me out. A ketone, acetone, and acetonitrile. If your professor is making you memorize, these are the ones that you have to know. And I won't draw them all out, but I'll show you some. So for example, DMSO, dimethyl sulfoxide, is a sulfoxide bound to a dimethyl. Notice that on the dimethyl, hydrogen is there, but it's not on the oxygen. It's sitting on the carbon. No fun. DMF, dimethylformamide. Form is a carbon like that. Amide, nitrogen, dimethyl, like this. So we have hydrogen, but it's not sitting on oxygen. It's not sitting on nitrogen. it's sitting on carbon. Ethers, you should know, ROR. A common one that you're going to see is THF, a cyclic ether. Acetone is just a ketone. And acetonitrile, might as well just draw that one out as well. Aceto is a 2-carbon chain, but the second one is a nitrile. There you go. Each of these are considered an aprotic solvent. And now that we see the difference, what can we tell about them? How will this help us with the reaction? Let's take a look at each one individually. Let's move this down here. For a protic solvent, it is useful for 2 reactions. Very, very important to recognize it's very important not to just rule one out. In the context of SN1 or E1, it's great at stabilizing the intermediates. That means your charged intermediates and your leaving group. And for E2, it's going to play very nicely with your base. So if we have a protic solvent, it's not ideal for an SN2 reaction. Not ideal for SN2. Now, if we have an aprotic solvent, then it's the exact opposite. It's ideal for an SN2, but it does not have that polarity, the protic intense difference in charge that you see with an O holding an H or an N holding an H. And that means it's not going to be good for an E2 or your one-type reactions, SN1 and E1. All right. If you're with me so far, what emoji should we ask for this time? Let me get a clapping hands emoji. And then we have one more piece to look at before we tie it all together with practice. And again, for even more practice, grab the worksheet. Just put worksheet in the comments, and you can get tons and tons of practice. I have SN1 versus SN2, E1 versus E2, and then, of course, choosing between, just going through all of them and having to figure out which reaction can take place. Last but not least on the checklist, we have the leaving group. Now, the leaving group is really just a formality. We just want to make sure that the leaving group will leave. And there's 2 ways that we can define a leaving group. One, will it actually break away? A carbon is not going to break off. A hydrogen by itself has to be pulled off. It's not going to leave by itself. And 2, if you somehow manage to kick it out, if it somehow manages to leave, will it stay gone? So 1, will it leave? And 2, will it stay gone? A halogen is a good leaving group, and that is the most common one that you're going to see. But sometimes you're going to see something like an OH minus, an N blank minus. These are bad leaving groups. But if that's the situation, you are able to do something like bribe it or attach something big to it to make it leave. So it's not a question of helping figure out which reaction, but rather, do I have to do some kind of step prior to that? But first, we have a question. I was told in class that aprotic is okay for E2. E2 reactions are not eliminated by an aprotic solvent, but rather if you have a choice between SN2 or E2, the protic will favor E2, aprotic will favor SN2. And the reason for that is in an aprotic solvent, because there's no way to stabilize the charges, that attacking molecule, that nucleophile or base, is going to be a lot easier to polarize. And the key behind an SN2 reaction is that attacker can polarize, can concentrate. So it'll take all that charges, concentrate, and then do one big attack because all the charges concentrated together. In a protic solvent, there's way too much partial charge. And if it tries to polarize, it gets pulled a little in this direction, a little in that direction, a little in that direction. It can't concentrate as much. So I hope that's clear, Ella. E2, protic favored. SN2, aprotic favored. So now that we've gone through the checklist, I want to show you how to do it in practice because, well, without practice, it's not helpful. So I'm going to show you each of the individual reactions. Make sure you grab the worksheet so that you can practice even more. And if you're not subscribed yet, what are you waiting for? Go ahead and hit subscribe as we jump into, here's what we're going to do. We'll take our checklist, and instead of figuring out which reaction can take place, we're going to figure out which reaction cannot take place. And by ruling out as many reactions as possible, hopefully the right answer will reveal itself by being the only one left. I'll show it to you in the context of each reaction with a quick review of the reactions, so that way you'll be armed for even more practice. The SN1 reaction is nucleophilic substitution. The 1 stands for unimolecular. And that tells me I have one molecule at a time. This is the rate determining step. The 1 is the rate order. And the simple mechanism for this reaction, to remind you, is the leaving group will break away and leave me with a carbocation intermediate. That carbocation, the slow step, is the rate determining step of this reaction. And then some kind of weak nucleophile is going to come in and attack, giving me the product that very likely is going to have to be deprotonated. And that's your final product. So let's see how this works in the context of a checklist by using the molecule that we started out with initially. You know what, let's take something a little bit more. Let me make sure this is charging so it doesn't die on me, because it likes to do that. Let's take something like this. So if I have a molecule that looks like this with a chlorine as a ligand, I start with my alkyl chain and I'm looking at my alpha carbon. The alpha carbon is the carbon holding the chlorine, and this is a tertiary carbon. Tertiary carbon tells me I will make a very strong and therefore stable carbocation. And if I have a stable carbocation, I cannot rule out the 1-type reactions, but at the same time, having a tertiary carbon holding the leaving group, it's way too sterically hindered. It's too bulky for an SN2 reaction. So I rule out SN2. I do notice that I have beta carbons, but we're looking at this in the context of SN1. So let's, oh, wow. I didn't actually give you anything to react it with. So let's work on that. We're going to use, we'll put H plus and CH3OH. There we go. The next thing I'll look at is my attacker. Now, if you remember in the discussion of nucleophile versus base, I said that the attacker is going to be negative or partially negative. Typically, your attacker is drawn up here, but all I have is an acid catalyst, a proton. That's not an attacker. That's not negative or partially negative. So what do I do? Well, we're not given an attacker. All we have is a solvent. That would be a problem until you realize, this is a solvolysis reaction. Solvolysis, solvolysis. The solvent is going to break, the solvent is going to attack. And typically in your SN1 reactions, your solvent happens to also be the attacking molecule. But because the solvent is neutral, it's weak, it's calm, it waits. It does not have the power to kick out a leaving group. And that means we rule out E2 because it's not going to be a strong attack. Next, we look at our solvent. We've already identified that it's CH3OH. H is sitting on an oxygen. That is a polar protic solvent. In the context of SN1, it will stabilize the carbocation. It'll keep everything happy, so we're good. And the leaving group is chlorine. Halogen is a good leaving group. Not worried about a thing. So let's go through this reaction. I'm going to show you the mechanism for this reaction. But if, after I'm done, if you want to see a shortcut for how to come up with a product without having to waste time on the mechanism, put mechanism in the comments, and I will start with the mechanism first. Chlorine leaves, giving me a carbocation where the chlorine left. Chlorine is off somewhere in solution. I don't care about it, so I'm not going to show it. Next, I have my CH3OH, my solvent molecule, also acting as my attacker. The oxygen is going to use its highly electronegative neutral electrons, but it's partially negative, to attack the carbocation and form a new bond right there. This is going to give me a molecule that looks like it wants to be the final product, except our final product should ideally be neutral. And this final product is not neutral because it's got a lone pair positive charge. So we have to change that. We have to fix it. And the way we do that is another solvent molecule is going to use its lone electrons to grab that hydrogen, give oxygen back its electrons. And that will give me this right here with just an O, CH3, 2 lone pairs, no charge. So we have our final product, but we took our time and worked through the step-by-step mechanism. And on your exam, you don't have that kind of time. So here is the shortcut. Let's do this whole thing again. I'll let you see the mechanism, but I challenge you that unless the professor asks for a mechanism, don't show it. So sometimes the problem will say, complete, fill in the missing whatever, or complete this reaction. But if they don't ask for a mechanism, do not waste your time. Here is what I want you to do instead. Do a quick analysis of the checklist. Determine that it's going to be, in this case, it can be an SN1 reaction. We have not ruled out E1. I'm simply showing you the SN1 version. And all you're going to do is as follows. I confirm it's an SN1. So I will redraw my carbon skeleton exactly as I see it. I will not draw my leaving group, so I cross it out. In its place, I draw a new bond where the leaving group used to be, and then I add my nucleophile or my solvent. But if it's a neutral solvent, then I want to take an extra step and do this. So this is what I have for my solvent molecule. The backpack trick, which I'm going to link in the description, is as follows. You cross out the hydrogen atom because that ultimately is going to get deprotonated in the mechanism. You find your electronegative atom and attach that where the leaving group used to be. And then you grab the backpack, everything else that was attached to the electronegative atom, in this case OCH3. Same exact product, but no time wasted doing the mechanism. Question. Is it possible to obtain a halogen from OH through SN1 or SN2? Yes, it is. And why don't I show you a problem right now? If I have a molecule that looks like this, we'll make it very similar, but this time I'll give you an OH and react it with HCl. In a situation like this, remember I told you halogens can make good nucleophiles but weak bases. So let's take a look at our checklist. And the checklist is as follows. Alpha carbon, tertiary, so we rule out SN2. Beta carbon, we're not looking at unless we know we're going with an elimination reaction. But I do notice that I have my beta carbons there, so we're good. Attacker should be something negative or partially negative. All I have is HCl. HCl is an acid, not a base, but recognize that in the context of a nucleophilic substitution, chlorine can be a nucleophile because HCl is a very, very strong acid and will give you 100% dissociation in solution to give you H plus and Cl minus. Cl minus as an attacker can be a nucleophile, not a base. That means I rule out E1 and E2, leaving me with an SN1 reaction. My solvent is not given, but we're going to assume it's something that HCl can dissolve in, so I don't have to worry about it. My leaving group is OH. OH is not a good leaving group. OH minus is a very strong attacker. We've already said that. So we're going to have to bribe it. If the oxygen reacts with an acid, OH reaches out and grabs that proton. That will give me a molecule that looks like this, where now I have an OH, another H, lone pair, and a positive charge. Now I have a good leaving group. So OH minus is a bad leaving group, but a water molecule is very, very stable on its own. And if I allow that to happen, look what happens in solution. I get my tertiary carbocation, and then in solution, I have an OH, another H, and 2 lone pairs of electrons. The 1 lone pair from the bond, the lone pair that it had. That is a good leaving group. So I bribed it. It's gone. Cl minus will take advantage of this situation and attack. And that is going to give me a Cl right there. And that is how you got a halogen from an oxygen, where typically you're used to seeing the oxygen attack and get rid of the halogen. Guillermo, let me know if that helped, because that was a very, very good question. And what I want to do is take a very similar reaction, but now actually, why am I showing the checklist? Before the checklist, let's quickly review E1, because I want to then go through the checklist for E1. E1 stands for elimination. The 1 is unimolecular, but the E is beta E, beta elimination. And what's going to happen in a reaction like this is when I have a molecule with a leaving group, let's just keep it generic for a moment. The leaving group is a good leaving group, so it's going to leave. If it doesn't leave, then we're not going to have an E1 reaction, because we need that carbocation intermediate. That is the rate determining step. Then a base will come in, but instead of attacking at the carbocation, at the alpha carbon, the base is going to reach for protons nearby, collapsing those electrons up towards the carbocation and forming a pi bond right there, like so. This is one option. I could have had more, but this is the one we're going to show for now, and I'll work through a problem, another problem after. So this is the overview for the elimination reaction. Let's see how that works in context of the checklist. A very, very common E1 reaction that you're going to see is similar to what we just did. So let's draw this molecule with an OH, and we're going to react it in H2SO4. So, and we're going to add some heat. Heat will help stabilize the formation of a pi bond over nucleophilic substitution, but it doesn't rule out SN1 completely. It just tells us that we're more likely to see elimination. So what do you think? As I start working through the checklist, let me know in the comments if you think this is, well, I already told you we're about to do E1, but let me know what you would have thought. Would this undergo SN1, SN2, E1, or E2? And let's see. The first thing I look at is my alkyl chain. I see that my leaving group is sitting on a tertiary carbon. That means I rule out SN2. And then I also look at my beta carbons, because I want to make sure that if I have to form a pi bond, I know how to differentiate them. I marked rule 3. We're going to come back to it as needed after. My attacker, well, there's no attacker here. All I have is H2SO4, which is a source of protons in solution. It's an acid catalyst. A lot of students will think that if H2SO4 can dissociate to give me H plus and HSO4 minus, then this right here would be my nucleophile or my base, and the answer is absolutely not. If you think a halogen is stable in solution, HSO4 minus is so much more stable because it has resonance that this is not going to participate. The moment it breaks away, it says, I'm done, goes and takes a nap somewhere, and completely doesn't care if the world is falling apart around. So HSO4 is gone. And if your professor shows HSO4 grabbing a proton, which I have seen way too many times, I'm going to put this very, very nicely and very respectfully. The professor is wrong. It's not HSO4. So what is my attacker? Well, HSO4 does not exist in a vacuum. So if no solvent is given, then you assume that you have some kind of aqueous solvent, or let's not forget what we have here. This is an alcohol. This alcohol could be my solvent. So it'll either be another alcohol or a molecule of water. I just realized if I give you an alcohol, I probably want to put some mild H2O, So otherwise you'll be using this, which I have seen, but we're not trying to get that tricky today. And that would be my attacker, either the alcohol or the water. Sometimes you'll see a mix of both. I've seen reactions where the professor will put CH3OH/H2O. Come on, pick one. It's neutral. It's going to allow carbocation. It's not going to allow an E2. That just needs something too strong. So we ruled out E2. Now we're stuck between SN1 and E1. The solvent is polar protic, either the mild H2O or the alcohol, and the leaving group is a bad leaving group, which is fine because we have the ability to protonate with an H+. Let's just work on mechanism down here. So right now we have an oxygen, a hydrogen, another hydrogen, lone pair and positive charge. We turned OH into a good leaving group. So we kick it out. This is my slow step to form a carbocation right here at the tertiary position. Water is off somewhere. And now, because of the heat, I will favor E2. The question is, which beta hydrogen do I grab? I have beta hydrogens right here. I have beta hydrogens right here. And because that's a methyl group, this is actually the same thing, so I'm drawing them in the same color. Which one I grab? The answer is both, and I can show two different reactions. If I grab the blue, I know why I'm drawing an OH minus. I'm trying to draw a water molecule. If my water chooses to grab a blue hydrogen, then I grab, collapse, and get something that looks like this, with a light blue bond right here. If the OH minus instead grabs a green hydrogen, I keep saying OH minus, water, neutral, grabs the green one, collapse, I would get a molecule that looks like this. So the question is, which one is it? Is it the one on the right or the left? And the answer is both. What you're looking at here is two different products where one is major and the other one is minor. And if you watch my video on Zaitsev's rule, you'll see that the more substituted the pi bond, the more stable, which gives us the major product. And this one right here, the major is tri-substituted. The minor is di-substituted. So we have our major and minor product for our two elimination products. Once again, what if you want just the shortcut without drawing out the whole mechanism? Very simple. If I have a molecule that looks like this, and I'm asked to react in H2SO4 with heat, I go through the checklist, I determine what's going to happen. I redraw my carbon skeleton exactly as I see it. I cross out my OH because I know it was protonated and left as a leaving group. And then I identify that I have a beta carbon with hydrogen right there, draw in a pi bond, plus identify your other beta carbon, light blue, identify the other beta carbon right there for a pi bond like this. And that is how you get the E1 product without the mechanism. Question, can we do one where the attacker is on the carbon chain? Nikki, that is a very good one. Let me see if I can get a couple of yeses in the comments if you want to see an internal attack. So let's do a quick overview of the SN2 reaction. SN2, the S stands for substitution. The N is nucleophilic, and the 2 is bimolecular, telling us that it's two molecules reacting at the same time for a one-step reaction. In an SN2 reaction, if I have a molecule with a leaving group, a strong nucleophile will come in, attack, kick it out, and that's it. There's only one step, no intermediates whatsoever, and that's it. So let's see how to do this with the checklist. And I see quite a few yeses in the comments. So let's trying to think, or SN2. I'm going to have to make this really tricky. Give me a moment. Let me think. I love making up problems. Okay, so if we have something like this, an OH and a Cl, let me just think of the conditions that will make this happen. Let's throw in some DMSO. There we go. We're looking at our checklist, and we have our alkyl chain, which is this thing. But I'm torn between having an alpha carbon here or an alpha carbon here. The alpha carbon is the one that holds the leaving group. And we've already seen where OH can be a leaving group. But with OH as a leaving group, we have to protonate it, and that will require an acid catalyst. So two things I want you to notice here. One, there is no acid catalyst. And two, when you're comparing two different options, if I have to protonate and bribe the OH minus, I can kick it out. But if I have something that is a better leaving group, I'm just going to go with the easier reaction because easier is faster. The easier the reaction, the faster it's going to be. So this right here is my alpha. And this alpha is a primary carbon. I cannot form a primary carbocation. So I'm going to rule out SN1 and E1. Next, I'm looking at my attacker, but nothing is given. In the SN1 and E1 reaction, if I did not have an attacker given, I looked at my solvent. Now, if my solvent is polar, protic, water, alcohol, ammonia, it can also be the attacker. But in the case of DMSO, it's just there. It has no interest in reacting. It is not going to do anything for the reaction. And so the attacker has to be inside the molecule itself, which right there, that is my attacker, and that is my leaving group. Now, this attacker is not very strong, but I don't have any other option. And as an attacker like this, it's neutral on the chain. It's less likely to abstract a proton and more likely to just grab this right here, the carbon. So we're looking at an SN2 reaction. Moving down to the solvent, it's polar aprotic. So again, SN2 over E2 when dealing with an aprotic solvent. So again, I'm favoring SN2. I haven't completely ruled out E2, but I'm leaning more and more and more towards E2. And with chlorine as my leaving group, I do have a good leaving group. So now we have to figure out what the reaction is actually going to be. We kind of know what it is. We know that the OH is going to attack the chlorine. Move that alpha out of the way so I can draw it. And typically what people will do is try to draw the mechanism like this and figure it out. I find this to be confusing because I don't want to make a mistake when I redraw it. So the first thing I do in an internal attack or anytime a molecule needs to be twisted the other way is I do what is called a redraw. I know, very complicated, very advanced. I'm looking to see how it's going to line up for that attack. And I see that my carbon chain is 1, 2, 3, 4, 5. So I'm going to just twist it because remember, these are all sp3 carbon atoms and they can fully twist however they want. So I have right here, 1, 2, 3, 4, 5. And then I wanted to number it the other way. Hang on, let me show you why. I want it to look pretty. I want the one here, 1, 2, 3, 4, 5. Because then I put the OH right here. I put the Cl right here. And is this not so much more obvious exactly what happens here and why, but also what it's going to look like as a result? So I have 3 and 2, 4, 5, 2 to 1. 1 is bound to the oxygen. Oxygen still has a hydrogen. There is a new bond here, and then Cl is off somewhere in solution, which we don't really care about. This is nearly my final product, but it's got a charge, so I'll just bring another one of these molecules. And so HO 1, 2, 3, 4, 5, Cl. I need something to deprotonate, and without a solvent, this is all I'm left with. And this will give me my final product, which is now a 6-member heterocycle. Hetero means it has an atom other than oxygen in the ring. Let's make that a little prettier. An oxygen right there. It's got its lone pairs back. It's perfectly happy. And there's my SN2. So who had asked for that? I think there's someone in Nikki. Yes, Nikki. What do you think? Internal reaction. Scary looking at first, but hopefully it looks kind of simple. And yes, this is a cyclic ether. Absolutely correct. Would this only happen if an attacker is not given? If the attacker is given, I would have to use something else. But if I don't have the attacker given, then this is the option here. Let's jump on over to E2, because I don't want to leave you hanging there. So for E2, just like E1, we have the beta, although there's no beta E2 in the name of the reaction, because that would be too complicated, I think. Beta elimination bimolecular. And just like the SN2 reaction, bi just means two molecules reacting at the same time. So let's take a look at a simple version of this reaction. If I have something like this with a leaving group, and I react it with a very, very strong base, the base, I don't know why I'm showing so many hydrogens, we just need one of them. The base is going to come in and in one fell swoop, grab the hydrogen, collapse the electrons, kick it out, and there we go. There's my pi bond. So let's take a look at how the checklist applies with a specific reaction. So let's look at a carbon chain like this with an iodine, and we're going to react this with NaOH in H2O. So let's begin with the alkyl chain. The alkyl chain has an alpha carbon with iodine sitting on a tertiary, at the tertiary position. I immediately rule out SN2. It's too crowded. The beta carbons, I notice that these two are exactly the same. This one is different, but I have a couple of different options. My attacker is pretending to be neutral, but anytime you see Na+, it is just a positive spectator hiding the fact that I have an OH-. OH- is strong, negative, will not allow a carbocation intermediate, and that means I'm going to rule out my SN1 and E1, leaving me with just E2. My solvent is H2O, which is a protic, a polar protic solvent, which is going to favor E2 in a two-type situation, and I have a good leaving group. So the iodine, well, it's not going to leave on its own. We'll have our OH- come in and grab, just like before. I have the option of choosing the more substituted or less substituted beta hydrogens, because these are all viable options. If the OH- grabs this one, collapse and kick out the leaving group, then I get my first product. I'm going to run out of room there, so I'll just try it right here. I get my first product, which has a pi bond sitting right there. But if the OH- instead grabs this one to kick it out and kick out the iodine, I get my second product, which has the pi bond right here. Once again, I have my major and I have my minor. Both are viable products. Okay. Question. Can we do a question? Can we do a question? Is ring opening with a protective alcohol? Protecting groups are in a different chapter, but how about we do a ring expansion? If you want to see a ring expansion problem, go ahead and put expansion in the comments. Also, remember, for a copy of the session notes from today, all you have to do is go to layerforsci.com/orgolive, and you're going to get today's session notes, the notes from previous sessions as well. For a copy of my brand new substitution elimination midterm practice worksheet, not available on my website, just comment worksheet, yes, even if you're watching the recording, and I will make sure you get a copy. Question first. Why it's not E2? This is E2, unless I missed when you typed that question. likes to give us Newman in my elimination videos on this channel, and email me if you can't find it. I actually have a Newman, E2 Newman video, so let me know. When do we have to consider E, Z, cis, and trans? If you have multiple options, the more stable, so you have to show all of them, but the ones that are anti are more stable than the ones that are together. So trans is more stable than cis, but you would have to show all of them as an option. And why it's not SN2 is because we have a protic solvent rather than aprotic, which favors SN2. And because we immediately ruled out SN2 as soon as we noticed the leaving group is sitting on a tertiary carbon, because that is way too hindered. I see expansion in the comments, so let's go ahead and try this problem right here. We'll have, let's see. So we'll have something like this with a chlorine, and you're asked to react it with H2SO4 and heat. In a situation like this, we want to figure out, we're definitely going to need more room. Hang on, let's move it down. So start thinking about it. Let me know in the comments if you think this is going to undergo SN1, SN2, E1, or E2. And we'll work through the checklist so you can see how to apply it. All right, so the checklist says alkyl chain. I have a secondary leaving group. Secondary tells me nothing. Nothing, nothing, nothing. I can't rule out the twos. I can't rule out the ones. If your professor is giving you a secondary leaving group, they're trying to make your life hard. I also notice I have beta carbons, so if I need to do elimination, I will keep that in mind. Next, I look for my attacker, and I don't have one. All I have is H2SO4, which I immediately recognize is a source of protons. It is an acid catalyst, but I have no attacker. What I do know is if I don't have an attacker given, I don't have a solvent given, and there's nothing here that could act as a solvent like an alcohol, then this is an implied aqueous solution they decided to just leave out for no reason. And so now I see my attacker is water. Water is the aqueous solution that they chose not to tell us about. My attacker is neutral. It's weak. It is not going to kick out anything. So I will rule out my SN2 or E2. We have to wait for a carbocation to form. Then I look at my solvent. It is polar protic. Knowing that it's an E1 or SN1 reaction, we know it's going to stabilize any charged intermediates, which works out for SN1 and E1. Halogen is a good leaving group. I'm looking at SN1 and E1, but here's heat. Now, here's what I want you to recognize. Anytime you see H2SO4 heat, I want you to think E1. Don't memorize it, recognize, because you've practiced it a few times. So we are looking at an E1 reaction. And now for the tricky part. With an E1 reaction, the first step is the carbocation formation. I don't feel like redrawing this, so we're just going to do that. All right, so the carbocation is going to form at the secondary position. Now, here are the tricks that you want to recognize. And the tricks are as follows. 1, if you have a secondary carbon, a secondary carbocation near a tertiary carbon, you're going to get a hydride shift. Secondary carbon, carbocation, tertiary carbon. If you have a secondary carbocation near a quaternary carbon, you're going to get an alkyl shift, like a methyl shift and whatnot. This is in a regular situation. Now, here is the next trick I want you to recognize. If you have a secondary carbocation near a ring that is less than 6 carbons, look for an upgrade. A 6-carbon ring is ideal. 5 and 7 are kind of okay. 4 is not really good, and 3 is terrible. So if you have 3, it wants to be 4. 4 wants to be 5. 5 wants to be 6. A secondary carbocation near a non-ideal and less than happy ring is going to open. You're going to get an upgrade from a 5-membered ring, in this case, to a 6-membered ring, because notice I have a 5-membered ring right there. If you like this shortcut, and I'm going to show you how to apply it, let me see party emojis. Let's see party emojis, and I'll show you a shortcut for this as well. Not really a shortcut. I'll show you a sanity-saving trick, or the way that I like to do it, that I find so much easier than how professors teach it. In order to do this ring expansion, what I recognize is that I have a carbocation sitting next to a tertiary carbon. So I look at the tertiary carbon because that is where I would like to have the carbocation, and I want to find the carbon next to it. So the carbon next to the tertiary carbon is the one that's going to move. I can move this one or this one. They're both exactly the same. So I'm just going to grab this one right here. And here's what's going to happen. I have these two electrons make up this this single bond. But when these two electrons as a bond moves over here, this electron never left the carbon it's attached to. It's this one that broke away. And so the trick I want you to show, it's going to move like this. So here's the trick. Cross out the bond that's breaking, draw dots to how you're going to have your bond. And do not try to draw the next step. I see people trying to create the right shape ring, and then they miss something. The carbocation goes in the wrong place, and everything just gets messed up. No. Just redraw it exactly as you see it. So what I see is what looked like a 5-membered ring. And I'm going to just draw some dots to remind me I had a bond there that is gone. This right here is there, and this is my new bond. The carbon that lost the pi bond and got nothing in return, the one where the dots lead to, that's my new carbocation. And now that I have a very, very clear, weirdly drawn picture of what I'm looking at, I'm going to number and redraw. I promise this extra step is going to save you time. Yes, more steps, less time, because it's so clear. I'm going to number it randomly 1, 2, 3, 4, 5, 6, 7. And notice that the ring itself is 1, 2, 3, 4, 5, 6. So it's a 6-membered ring. I'm going to acknowledge that and completely obliterate my molecule. Just cover it. Don't cross it out on your exam. Draw a 6-membered ring, and then look back at what you have. This I find so much easier. The ring itself is 2, 3, 4, 5, 6, 7, and then do kind of like a paint by number. What does 1 have? What does 2 have? Carbon 2 has a methyl group, carbon 1 coming off it. 7 and 2 are attached to each other, which they are. That new bond is between 3 and 2, which they are. So it's completely different, but because I numbered it, I'm missing nothing. This is just a redraw. Very, very big time saver. Carbocation on 7. Now at this point, let's not forget a secondary carbocation near a tertiary carbon will give you a hydride shift, which means I got to shift that hydride to give me a more stable carbocation, now sitting at the tertiary position. At this point, because I'm doing elimination, I look for my beta hydrogen. So I have these two here and these two here. In this situation, it doesn't matter which one because there's symmetry in the molecules, so I can grab either one. We determined water as the solvent, and so that's going to come in, grab the hydrogen, collapse the electron towards the pi bond, and my final elimination product here, I guess I should have pointed out that I also have beta hydrogens here, but I was going for the more substituted, more stable product. So that will give me a pi bond right there. But if your professor asks for all of them, this is your major product because it's more substituted. And then this right here is your minor product. How do I pull the hydrogens from up top? That would be right there. Nadia had a very similar problem to this on homework. Nadia, given what I showed you today, does it seem so much, not necessarily easier, but more doable and more approachable? So this question for Nadia and everyone else, let me know if you like this type of problem. And I do have similar problems to this on the midterm worksheet as well. So make sure you grab your copy. So just put worksheet in the comments and I'll send you the link. look at the pinned comment for a copy of the notes from today's session so that you can go back through all of that as well. And then the worksheet is just tons and tons and tons of problems. Eddie says, yes, much easier numbering the carbon and so winging it. No, 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 no. Absolutely no winging it. This topic is way too hard and you have way too much on the line to wing it. I want you to know, and I want you to have a step-by-step to do it exactly right. Okay, guys, this concludes today's session. This is a very, wow, we went quite a bit over my intended hour. Hopefully the extra time was worth it. Make sure you grab a copy of the worksheet by commenting worksheet below. Grab the notes from today by checking the pinned comments. And if you're looking for even more help, especially covering everything in order, Organic Chemistry 1, Organic Chemistry 2 in this format with lots of practice, as well as the ability to ask me your daily study questions, come work with me in the Organic Chemistry Study Hall. The link to sign up is leahforsci.com/join, and I hope to see you there. Once I log off, I will be able to hang out in the comments, I believe, for a couple of minutes. So go ahead and type any comments, any questions that you have. I will go ahead and wrap this up. I will save the notes. I will email it for anyone who signed up at leahforsci.com/orgolive. And then I will see you next week. Oh, happy Thanksgiving to all my US students who are celebrating. Next week's topic is very likely going to be synthesis. So make sure you mark your calendar, same time, same place. I'll see you guys soon. Oh, also, I am thinking of doing 1 or 2 pre-final exam reviews, just going through everything. So let me know if this is something you're interested in. Email me, because once, let me know here if you're interested, or email me, and I'm rambling. I will post some polls and some notices on the YouTube community tab, and that we will get all that organized. All right, guys, have a wonderful evening and take care.